the distance formula. Okay, so say you have a point right here, another point right here. Let's label the first point, I don't know, x1, y1, how about? Let's label the second point x2, y2. And we want to find the distance between those 2 points. Do you think this has any relevance to your everyday life? Probably. That GPS that you love so much, your navigation on your phone or in your car, uses to locate your position on the earth, it's got to know something about distance, right? And it uses a more complicated version of the distance formula, a similar version but more complicated version of the distance formula that I'm about to show you. All right, so we want to find the distance between these 2 points. Let me draw a little line segment between them, because really what the problem breaks down to is finding the length of that line segment, right? Well, as you might imagine, I could turn this into a triangle pretty easily. So I'm going to drop, from the second point, I'm going to drop a perpendicular. Now, what is it going to be perpendicular to? Well, let's just call it vertical for now. And then from the first point, I'm going to throw in a horizontal line segment. So now it makes sense calling that guy from the second point a perpendicular, because because the horizontal and vertical line segments will be perpendicular to each other. And then you can see the triangle I've created, and it'll be easier on the eyes if I erase the extra stuff. So erase that, erase that. So I created a right triangle.
So what familiar theorem can I use to find the length of that black line segment there?
The good old Pythagorean theorem. Now, what I like to do, I like to ease the strain on your memory. There's a lot to memorize in math. And one way to make it easier to memorize things is to relate what you're learning now to what you've learned in the past. So what you've learned in the past is, remember the slope formula? So we're not going to use the slope here, but you probably have it in your brain somewhere. Do you remember that slope? We used m to represent slope, and we called it rise over run, right? Remember that? So if you wanted the slope between 2 points, it's a ratio. It's the rise, the vertical rise from one point to the other, over the horizontal run from one point to the other. And the bigger that number, the steeper the line, right? So you all remember that. So if I were going to label one of these legs, the shorter sides of my triangle, run, which side would it be, the horizontal or vertical? It would be the horizontal, right? So the run from x1 to y1, x1, y1 to x2, y2 rather, would be the horizontal distance between the points, right? The left-right distance between the points. And then the rise, hopefully it's clear, would be the vertical piece, the vertical side. And then that makes it pretty easy. If we call that hypotenuse, which is the distance we're looking for, if we call that, instead of calling it C, let's call it D, then what does the Pythagorean theorem say about these 3 pieces of information? You could make a formula out of the word, right? The run squared plus the rise squared equals d squared, right? Isn't that the Pythagorean theorem? I'm going to write it this way. I'm going to put the d squared on the left. D squared equals run squared plus rise squared. Does everybody see that I'm relating this? You know about the run and rise, the rise and run from the slope formula. So why not take advantage of that knowledge to kind of make this a little bit, and the fact that you know about the Pythagorean theorem already, why not take advantage of that previous knowledge to create the distance formula? Now this isn't quite the distance formula because I need d, not d squared. So what do I do to both sides? Take the square root, yeah. So, and then you've got it. You've got the distance formula. Now, it's the square root of the whole thing, right? You can't split up the square root over addition. So you get d, and you won't see the formula written this way in any books. This is my own little idea. D equals the square root of run squared plus rise squared. But I think that's a neat way to remember it.
Did you say d equals 1 plus rise?
1?
Run plus rise.
No, because the square root, I'm glad you asked that, because it's a very common mistake. The square root does not split up over addition. So you can't individually take the square root of run squared, and which if you could, it would equal run, but you can't split up the square root over addition. So no, that's the formula. You can't split it up anymore. Okay, so that's a good way to remember it. Now, what are you going to see in other books? Well, you may remember from the slope formula that you developed in previous classes that the run is really the difference between the x's, right? x2 minus x1. So the run squared would be x2 minus x1 squared. Plus, okay, what's the rise going to be in terms of y2 and y1? Yeah, well, and you could actually flip it around, make it y1 minus y2. It doesn't matter because you're squaring it out. If you get a negative there, you're going to square it out anyway. But you're used to calling the rise from other classes y2 minus y1. So this is the formula. If you prefer this one, this is the one that the book will give you. I don't care how you get the distance. I don't care if you think about it, the distance formula is just the Pythagorean theorem coordinatized, isn't it? So if you just derive it the way I just did, that's fine. If you memorize this last formula or the formula before it, that's fine. Just be able to find the distance using essentially the Pythagorean theorem, right? So let's practice that. Okay, so in this example, let's use the distance formula to find the distance between the 2 points 5, -2, and -7, -8. So just like with any other formula, in the homework, if you write it down every time you use it, you'll memorize it, and you won't even know you did it. And by the way, here's another a version of the distance formula that I really like. Another version of the distance formula says that d is equal to the square root of the run squared plus the rise squared. Okay, so we want to find the distance between the 2 points. D is going to be equal to the square root of, okay, what's the run going to be? Just don't actually compute it. Just let's write down the arithmetic. It's going to be the run squared. Okay, what is the run? There's two ways you can think of it. Okay, so I'll think of it that way too. -7 minus 5. Isn't that the run? And then you square that underneath the radical? Okay. And then plus, what's the rise going to be? Yeah, and actually you could do it. I like to practice to be consistent with the order of the selection of the coordinates. So you selected -7 first over here. It's a good habit to be in to select the other coordinate from that same first point first. But again, if you didn't do it that way, it wouldn't hurt you here. When you calculate slope, though, you'd get the opposite sign of what you're supposed to get. So -8 minus what? -2, right? So write it down like that, and then you square the whole thing. Put the extra set of parentheses around the -2, because it looks funny if you have x minus a -2 without the parentheses around the -2. All right, let's compute it. What's -7 minus 5? So you get -12 squared. You need those parentheses around the -12. When you don't have the parentheses, it's the opposite. You might be thinking it's 144, but when you write it without the parentheses around the -12, it's actually the opposite of 144, -144. Okay, and then plus what? -8 plus 2, right? So -6 quantity squared. Yeah? Okay, and so we get the square root of 144 plus 36. What's 144 plus 36? 180. All right, let's see if that simplifies a bit. Let's do a little factor tree over here. So you get the square root of 180 as your distance, by the way. But be in the habit of simplifying radicals. What two numbers do you think of that multiply together to make 180? 90 and 2, okay. That's one way to do it, right? And then what numbers make 90 when you multiply them? You always think of interesting combinations, Max. And then 30? 15 and 2. And then 3 and 5. Okay, so you just have two 2's, right? So 2 squared. Whoops. 2 squared. And then 2 3's? times 3 squared times 5. Make sure that's right. So what is that? 4 times 9? 36 times 5, I think will get you 180, won't it? Yeah. So just double check it, right? Okay. So we want to simplify that radical then. So we can think of it as the square root, yet more practice with simplifying radicals. The square root of 2 squared times 3 squared times 5. What can you pull out?
2 and 3.
Yeah, so you can pull out a square root of 2 squared, which is 2, a square root of 3 squared, which is 3, so 2 times 3, and you're left with a 5 underneath the radical. What does that simplify to be?
6 times the square root of 5.
6 radical 5 units, right? We didn't specify units, but if it said the units are in inches, you'd say 6 radical 5 inches. If it asks you for a decimal approximation, make sure you can do that on the calculator as well.